Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everybody, and welcome to our panel on cloud applications of the future. A few notes first before we begin, and then I'll do the introductions for our panelists. We have no break between our panel and the next session, so I am going to be ruthless on time, and we'll move forward right into the next session after the panel wraps up. A few words about the panel. When thinking about options for panels, we wanted to be consistent with the theme of this workshop, and that is looking at the future of the cloud, in particular the applications that the cloud could enable. And I challenged our panelists here to actually think about the devices, the way they interact with the cloud, and how that would change over time, and not focus on VMs or performance or some of the hard but relatively mundane things we have to wrestle with over the next couple of years, but to look out into the future. And I would engage you as the audience to actually engage with the panelists, trying to understand their thinking, trying to understand the research challenges to actually make their vision a reality. And I was very pleased when all the panelists that we invited, I chose people I thought were creative and actually very forward-looking thinkers, all accepted. So let me make some introductions here before we get started. Paul Watson from the University of Newcastle, Bertrand Meyer from ETH Zurich, Marty Humphrey from the University of Virginia, Savas Parasidides from Microsoft, and Rob Gillen from Oak Ridge National Lab. Two of our presenters will be using the slides. The other three will actually just be going verbally. And then I've asked them to talk for 5 to 7 minutes, and then we'll open it up for actually questions and discussions from the audience. So with that, I'll turn it over to Paul.
Okay, so do I need to do anything to have it up here?
And we can turn the projector on any time.
Yeah, it's gonna. Hey. Okay, so what I wanted to do is to use some examples of work that's in progress at Newcastle to try and illustrate some points about where I see the potential for cloud applications in the future, but also the issues that we really need to address if we're to use the cloud for these new class of applications that we're seeing. So I've been working on data for 25 years, and the main change I've seen over the last 2 or 3 years is being sensor-based data, real-time data. So 5 or 6 years ago when we started eScience at Newcastle, people would come along and they had spreadsheets or some database and they wanted to manipulate the information in them. Now they often come along and they've got some sensor-based information, they want to know what to do with it. And you can see some examples there just from projects that we're working on, which range from nowadays these systems where as you drive along, there's a system in the car that monitors everything that's going on. Environmental sensors, of course, are really revolutionizing that area of science. More and more medical experiments are now taking advantage of these lightweight medical sensors to do the real-time monitoring of patients. And in the transport area, you've got all these things which allow you to locate cars and people, and of course RFIDs, particularly in the logistics area. And you've also got people as well, who I think of these now as people generating real-time information, acting as sensors with their twittering and their use of email and texting and so on. And the thing that I came to the realization a little while ago was you could also see software as a service, an example of new sorts of sensors, because as people are typing, carrying out actions using these applications, all that information is available in real time to the application, if only you could do something useful with it. And that's the trick with all of these systems. You've got all this real-time information, and how can you use it? I'm going to use 2 specific examples to illustrate the issues. So these are from a project in Newcastle called SIDE, Social Inclusion Through the Digital Economy. So the idea here is to look at using technologies, new technologies, to help those people in society who traditionally don't benefit from technology. So older people, disabled people, and some sections of youth who are excluded, who are on the margins of society. And there's several strands, but one's on transport. And this is our electric car. So we've got 5 of these that travel around Newcastle. And I must admit my heart sank when Dan Reed in his talk this morning started talking about exactly what I was going to talk about, which was monitoring the car where it was, monitoring the battery and giving you information about how to navigate to a charger. But in this particular project, we're also looking at real-time telemetry to help older drivers. So the idea is, if you've got this information from the engine and you can process it in real time, there's all sorts of interesting things you can do with it. So this is just a real-time trace of somebody driving around Newcastle, and you can see the sorts of information you can get in real time, including things like not just the distance, but brake pedal pressed, how many times that happens. We get an event any time anybody does that, anytime they press the accelerator, anytime they change gear. And you can do two things. So you look at long-term trends for older drivers, so that if you ask older people what their main concern is in the UK, if you do surveys, the main thing is mobility. So keeping mobile is really important. And over time, people who are as they age, they start to run into problems. And one of them that you can detect with these sorts of systems is cognitive impairment. So, for example, vision problems. And one of the ways to do that is that if you find from these telemetry systems you get sudden acceleration and then braking, acceleration, braking, that often means that people's eyesight is starting to deteriorate and they're getting very close to the car in front before they notice it, and then they're slamming the brake on and accelerating again and slamming the brake on. So you can start to detect that. But you might think, well, you could do that not in real time. You just collect information in the car and over a period of time you might detect this. But actually another real problem is to do with drugs. So older people go to the doctors, they're given some drugs for a particular ailment, and to the surprise of the medic and the older person, actually it really impairs their driving ability. It has effect on their vision or their ability to navigate the car. And you can detect this in real time if you can monitor the information coming from the engine and start to see the trends which mean that they're not really driving particularly well. And you can do things like you can suggest that they go and try a different drug, or you can think about putting in assistance into the car to help them. For example, distance sensors, so that they get a warning when they're within a particular range of the car in front. So you've got this basic system. So this is an example. You want to send information from the telemetry up somewhere. You want to do this pattern matching analysis and reaction, which then feeds back down to the car, but also to other people, so medics, opticians, people who can provide assistive technologies. And in order to do this properly, you also need to integrate lots of information. So it'd be nice, for example, if you had some information about weather conditions, because that also affects driving. So real time, combining this information in real time really allows you to do more than you can with just one source of information. The final example is this one, which is about the connected home. So can we use these new pervasive technologies to allow older people to stay in their home for longer? Because from the point of view of older people, they would like to stay in their own homes for as long as possible. From the point of view of the state, it's actually very expensive to support older people in sheltered accommodation. So this is an example of a kitchen, which is in our lab at Newcastle, and this is all wired up with sensors. So the floor's got pressure sensors on it, so you know exactly where people are. There's RFID tags in all of the utensils and all of the ingredients that somebody might use in the kitchen. And there's cameras as well, which we can use to get ground truth data about what people are doing in the kitchen. And if I go to the next slide, which is somebody preparing food, you can see that on the back wall you can get information about a menu, and you might notice that the handles of the utensils are quite thick, and this is because they've got Wii remote controllers in them with the accelerometers. So all the time as these people are using these utensils, it knows whether if you pick the spoon up, it knows whether you're stirring with it or whether you're ladling with it, and so on. So there's all this activity recognition going on all the time. And the idea is, if you have all this information from all these sensors, then you can work out what task somebody is doing. And if, for example, if you have somebody with dementia, so if they have problems with their short-term memory and they get stuck in the middle of a task, then you can prompt them. So basically you build mathematical models of activity, you trace from the sensor information where they are in that activity, and then you give an audible prompt, say, or a visual prompt when they get stuck to go and carry out the next action. So for example, if they're making a cup of tea, they might get stuck at the point where they need to go and fill the kettle up with water, so you could tell them that they need to do that. And again, you get these sorts of this sensor information going somewhere to be processed and being fed back down in terms of advice to the individual, but also to other people. For example, if somebody's usually in the kitchen by 9 o'clock in the morning and they're not, you might want to alert neighbours or friends because you might want them to go and have a look, just check everything's okay. So we have an architecture for this. We've been building systems to do this sort of thing for 3 or 4 years, and we take the information in, we filter it, we do some real-time analysis, and we've got historic warehouses so that we can use machine learning techniques to look for key patterns. And we run this on our own servers using traditional database techniques. But the question is, could and should we move this to clouds? And so if you think about that, then why might we want to move it to clouds? So I think this is one of the key examples. You can have very thin clients. So you can see the car is just a thin client which is just sending information up. It doesn't actually have to do any processing. All of those applications can be done in the cloud. So you get simpler devices. They need lower energy, and you've got much more flexibility. So for example, you can add new applications and improve applications all the time. So if you look at the car, for example, so as I said, when Dan mentioned the navigation to a charger, that was rather deflated this morning, but actually it illustrates the point that using the same sensors in the car, you can do the navigation for to a charger. You can also give assistance to all the drivers in the way that I've described. You can do congestion avoidance, and there's people interested in things like dynamic congestion charging to try to influence the way in which drivers move on roads in order to reduce congestion. And you can do all that just with applications. You could do all that with applications in the cloud. You don't have to install anything new in the car itself. The same with the kitchen. We're not just doing work on helping people with dementia. We've also got some work with exactly the same kitchen on teaching cookery to young kids. Interactive cookery books which give you advice as you're going along for people like me who like to cook but aren't very good at it. And language learning as well. So task-based language learning through cookery. Cookery is actually something our education department's really very interested in. Then you've got scalability. So at the moment we've got 5 cars, but how do we get up to 50 million cars with the server that we have at the moment if we wanted to cover all of the cars in the UK? And the machine learning algorithms which take all of this data and try to look for these patterns so that they can provide good advice back to the individuals in the car, in the kitchen. So those are the potential benefits of clouds. There are also some challenges. So I think I'll stop with this last slide. So the question is, can clouds meet these needs? What about the latency, the bandwidth issues, the charges that you get for sending information in and out of clouds? Does that kill you compared to doing things more locally in the car, in the kitchen? And finally, are we all going to go and invent our own infrastructure to do this separately, or is there some sort of a common middleware for clouds to process this real-time information? So is there a Hadoop, for example, type of middleware for real-time clouds? Okay, thank you.
Thank you, Paul. And I'll introduce the next speaker, Bertrand Meyer from ETH.
So what do I have to do?
Hit escape on the keyboard.
Where is the keyboard?
And Alt-Tab.
Stealth keyboards. Is that you, sir?
That looks like it, yes. Okay, and this moves it back and forth. Okay. Okay. I appreciate very much the opportunity to be on this panel. I mean, I came here basically to learn. So it's a great honor to be suddenly promoted to expert. On the other hand, it's not something that would intimidate me in the sense that I've learned long ago that the best way to learn about a subject is to write and publish a book about it. So I guess being on a panel about it is the second best way to learn about a subject. Also, don't pay too much attention to these slides. I'm going to reveal the great secret that they were all prepared in the past 15 minutes. I mean, 20 minutes ago, there were no slides. So they're basically there for me to help me remember what I wanted to say. So what I want to talk about briefly is what the cloud changes with respect to the application of science, with a special emphasis on my field, which is software engineering. And this is also the opportunity to react to some of the points that were made in the fascinating keynotes that we've had over the past couple of days. So the message that we're getting is clear. The cloud changes everything. Research will move from experiment-based data-based. I think all three of the keynote speakers so far have said this in remarkably similar terms, and I would say it's a very compelling message. And Ed, in particular, Ed Lazowska, made a strong point that computational science, which is our way of interacting with other disciplines, will move from simulation to analysis of very large amounts of data. And I also perceive this message in this morning's keynote by Dan Reed, that inductive approaches will get a new boost. Inductive approaches meaning approaches that work from the existing data, can, as we would say as computer scientists, bottom up rather than top down, that is to say deductive. And this, as I mentioned this morning in a question to Dan, I'm not so sure about. Clearly there's going to be a number of benefits for science if the world of science indeed moves in the direction that the speakers unanimously described. We're going to be able to do science on a much bigger scale, much more realistic than what we've done before. It's going to be much more, we're going to have more realistic scenarios than those afforded by simulation. I'm thinking in particular of the very controversial today, but very critical to the survival of the world, issues of climate change, for example. We're going to have more surprises because when you get amounts of data that are larger by several orders of magnitude than what we've been used to, it's inevitable that we're going to get lots of surprises, of things that we did not expect. Also, the cloud, not automatically but naturally, favors more openness. And we've heard in particular about these astronomy experiments in which initially the astronomers were a bit reluctant to put their data in the public domain, and then they realized that everyone would benefit because the pie, the overall pie, would grow so much that everyone's slice would be bigger. And this is, in my opinion, a paradigm of many things to come, in particular in software engineering, to which I will come in a moment. Also, an important aspect of science, of good science, is reproducibility. By the way, this is one of the areas where computer science is traditionally very bad. Experimental software engineering has been very bad at reproducibility, and putting everything on the cloud, everything meaning programs and data, cannot but be extremely favorable to reproducibility. So these are some of the reasons to be enthusiastic, and I think you agree that there is a certain feeling of enthusiasm throughout this meeting and the presentations we have had. On the other hand, there are a number of issues, and so I don't think there are too many people in this group who are in software engineering. The few of us who are hardcore researchers in software engineering kind of meet in the back corridors and look at each other and exchange glances that basically mean, do these people know what they're getting into, right? So, everyone knows about problems of security, for example, but everyone seems also to assume that these things are going to work. Well, maybe. But if we are increasing the scale of everything, we are also increasing the scale of problems. And I don't want to get too personal, but when preparing my other talk, the talk that's coming in the next session, I actually crashed a PowerPoint doing something completely ordinary on a top-of-the-line workstation with a brand new version of Windows 7 with all the latest updates. So, well, if we... before we can get right the program that's going to be connected to your pacemaker so that it calls the ambulance if there's something wrong with your heart, before we get that one right, perhaps we must learn how to get PowerPoint right. So this was my bringing coal to Newcastle moment. So, the issues of reliability, of security, the issues of scalability are not going away, and someone at some point should worry about the software engineering aspect. Well, this is kind of my little comment on the issue of inductive versus deductive. These guys, somewhere between 1930 and 1950, convinced much of the world that the way good scientists work, at least in modern science, is not so much inductive. It's not like you look at the data and suddenly get the right idea. It's actually that you have an idea, right or wrong, and you try it out. And it seems to me that the case they made then is as compelling as it was then, and it's very dangerous to imagine that just by analyzing zillions of terabytes of data, you are just going to get good science. So to take an example from my own one of the research topics that I'm exploring, there's a very interesting activity at the moment in programming methodology, which is to infer program invariance, in particular loop invariance, right? And so the problem, contrary to what one might think, is not to find loop invariance. That's very easy. You want them, I'll give them to you automatically. The problem is to find good loop invariance, right? Because I mean, there's kind of cliche, almost joke example in the field, which is that the invariant that you're going to find is that your height, the height is always greater than the shoe size. So it's a typical mathematical property, right? Or the bad mathematical property. It's absolutely accurate. It's absolutely uninteresting. And this is the kind of thing that you risk getting if you just analyze the data and see what's there. So to take another example, I'm pretty sure that the people from Safeway who analyze our buying patterns, or the people from Amazon for that matter, pretty much know what they're looking for. And it's not that they just scan their zillions of data and find out what's there. So coming to the second and last part of this short overview, I talked about software engineering for the cloud. Now, what about the cloud for software engineering? It seems to me that people in software engineering have been rather shy in taking advantage so far of huge computing resources, cloud-based or not. And it's a pity, because there are lots of things that we can do. Now, one of the things that has happened in software engineering in recent years is the explosion of a field that used to be terrible and which is not so bad anymore. It's not good yet, but it's getting much better, or a little better. It's empirical software engineering. Empirical software engineering used to be terrible because we had bad data or no data, and experiments were not reproducible. And then suddenly this whole field has become exciting. Well, and when I say exciting, let me qualify this. I mean, our stuff is not sexy, right? We don't have smart cars. We don't have intelligent pacemakers. We don't have ambient kitchens. And our idea of multidisciplinarity in software engineering is when someone who does symbolic execution talks to someone who does testing, or someone who does model checking talks to someone who does abstract interpretation. That is how interdisciplinary we are. So exciting needs to be put in context. But for me, it's exciting. Suddenly we have these huge repositories of data going back 5, 10, 15 years, sometimes more, from Apache, from Eclipse, and also Microsoft has put a lot of data has made a lot of data available to researchers, and suddenly we can seriously talk about software as an artifact, as an object of empirical objective study. And this has given a new impetus to this old and boring field of empirical software engineering. And this is one of the areas where having much more computing power and much more storage and having a cloud-based architecture can make a big difference. Also, applications like model checking, like in particular SAT solving, could make much more use of cloud-based architectures. Proofs are, well, putting your code on the cloud is not going to turn an undecidable problem into a tractable one. But still, there's lots of things we can do by taking advantage of the cloud. And then the ultimate parallel problem is testing. And here is a little plug for some of the work that we are doing. There's an article in a recent issue of IEEE Computer where we describe this auto test tool that takes classes and tests them completely automatically by basically trying everything. It sounds silly, but actually it works very nicely. If you have enough computing power, it finds bugs, which is the only significant criterion for testing. So this is the kind of thing for which we can use distributed cloud-based architecture. The more the better. And I think we're going to see much more of this. And to finish, this is a plug for the next talk. So come in an hour or so, in 45 minutes or so, to room 1927, where I'll be describing this project that we have with another almost ideal application of cloud-based computing, that is to say a development environment where the program, actually all the artifacts of a software project are on the cloud. It's completely ridiculous that each developer should have his or her own copy, and then we run into these idiotic problems of reconciling everything. And so as a conclusion, or I'm not supposed to give a conclusion here, it's more a start of our discussion. There are lots of issues associated with software engineering and the cloud, but software engineering is absolutely fundamental for the cloud, and the cloud can bring new dimensions to software engineering.
Thank you, Bertrand. We can go ahead and shut the projector off now, guys. And I'll invite our next speaker, Marty Humphrey, to go ahead and talk now.
So when Roger told me about the panel, and I heard that Paul, my old friends Paul and Salvas were going to be on it, I was like, excellent. I'm sure I'll learn a lot. And then he goes, no, I want you to serve on the panel. And I said, oh, well, so things are a little more challenging to serve on the panel because, as Paul mentioned, the morning keynote in particular, I thought really summed up what I thought the next application should be, which is essentially that I want my applications to deliver the right information to me at the right time, in the right format, and in the right context, meaning on my particular device where I am, or on my laptop, or whatever. And Dan's application scenario where the phone doesn't call him unless he wants to pick up, I thought that was right on. That's what we want. And so my requirements for the next application, in some sense it's the application I've been wanting for a while, whether it now appears in the cloud or not, well, that's somewhat orthogonal. But those are the applications that I think we really need to be looking for. And so then I started thinking about what I thought were the somewhat less mundane reasons why these applications might not appear so quickly. In other words, the problems that I think the community should be looking at and solving. And so I came up with my top 5. The first that I think we really need to look into as a community is this notion of the push technology. It's interesting, one of my students told me that Amazon just came out with something this week which looks really intriguing. Can that be used in what context and by other platforms as a means to push information to us? I think that'd be really interesting to look into further. Just like with Paul, I want the real-time cloud. I want the real-time access to data. I want the real-time compute. That would be number 2 that I think we as a community need to develop. Number 3 is related to that. I want dynamic scalability on the order of seconds. We know right now it's on the order of minutes. It's on the order of 10 minutes. I want to scale and crank back down on the order of seconds. I'm not sure when that's going to happen. Number 4 is I think that the cloud boundary is too thick. And what I mean by that is you tend to be in the cloud or out of the cloud. You know kind of where you are. You know where the data is. You know in particular what cloud you're operating in. You know where things are. I want the barrier between clouds to break down. I want the barrier between cloud and non-cloud to break down as well. And then the last one, it may just be my particular pet peeve. In fact, I've had some conversations with various people here, and they've told me I'm completely wrong with this one, and I respect that. But the last one is I want to stop thinking about the economics of the cloud. I want to stop having to consider whether or not the cloud is economically feasible. I want to not worry about moving data into the cloud because it's off hours and it won't cost me that much. I don't want to keep having to go through this in my mind that is this worth $6? Is this worth $7? I want to stop doing that. I don't know when that's going to go away. I don't know when it's just going to be a given that it's economically feasible. I'm not quite there yet. And so those are the 5 things that I think we should, as a community, be looking at.
So Thank you very much for the invitation to the panel, first of all, Roger. It's very difficult to follow, all the keynotes and then what my co-panelists have said, because they've covered most of the space. Where I would like to concentrate is again on the future applications and the types of applications that I see the cloud enabling. When I say the cloud, it's just another name for what we've been talking about all these years around services. We've called it web endpoint node, and we called it grid. It's the main thing that we should really be considering is the type of applications that we want to enable. I'm with Martin. I don't know who told you that you're wrong, but I'm with you on the cost. I believe that very soon, in the next few years, perhaps decade, we're going to see the cloud, the virtualization aspects of the cloud being so commoditized that they're going to be so cheap. Companies are going to effectively offer additional services on top and offer the infrastructure for free. The costs are going down so fast that at some point they are gonna be free, and that's where I see the value coming. We see companies like Amazon innovating on the services front all the time, and they're going to be making money out of those services rather than the actual hosting of virtual machines. The interesting thing then becomes, how do you combine those services to build more interesting applications? Now the services become the middleware that spans an entire planet, and our applications have to be aware of that. We have applications now that will be built at global scale. Our way of developing those applications will have to accommodate for that. Where that leads us is to an ecosystem of services and applications that make it possible to bring islands of data together. Because everything just sits out there, it's easier to combine, it's easier to process, it's cheap to process, it's cheap to transfer, and so on. And this is where I believe the future value of applications is going to be. As some of you might know, I'm a very huge fan of semantics and knowledge representation technologies and knowledge processing, and I believe that going into the future, that's going to be a fundamental value of applications that are hosted in the cloud. How do we combine data in interesting ways without having to download it, to process it locally, and then perhaps share it with the community? Everything is out there. Companies are actually starting to attract, they're trying to attract customers to their infrastructure by offering access to data in a cheap and faster way. Amazon has started it, and I believe that, we were starting earlier, I believe that you saw a presentation from one of our preview technologies called Dallas. And I think this is a carrot for people, for a carrot that companies put out there to attract people to their platforms. But it's the interesting applications that we can build on top. Another discussion that I had a few days ago was this concept of building Foursquare type applications for data. It's great to go using Bing Maps and mass up the Foursquare nodes that people put for various places. So you can go, so the one that I noticed was on 520 bridge on top of Washington Lake. Someone had left a comment saying, do not try to cross the bridge when there are high winds in Seattle. And now that node is always there for someone to go and see. Imagine if you can start combining information that add value to give value to consumer. So imagine someone posting a note about a concert that took place at a stadium, and they post a note saying, I was here. You can have an ecosystem of data that is combined together to infer that that node was about the particular concert that took place there. Because we have both the spatial and temporal data from around the world to do that. You can do this for science. You can annotate data and make the data available. Everything that we've been talking about, provenance of information, it can be out there. And yes, of course, you access all that information from a variety of devices, a variety of devices that you use. So to me, the value of the cloud is that it can enable this type of applications, applications that focus on information, knowledge, and the sharing of those. I'll stop there.
So I've been spending the last week or so since Roger asked, thinking about this, and my background's probably a little different than most in that I'm not a classically trained scientist. I came from about 10 years in industry before I ended up at Oak Ridge. And as I've been chewing through this, I came up with sort of two examples, or two examples I want to use to sort of start my answer to the question of what I think the cloud enables. The first is Lego Mindstorms. Anybody know what Lego Mindstorms are? Okay, I love Lego Mindstorms. In case you don't know what it is, it's this toy that allows kids of, well, frankly, any age, I'm learning, to follow sort of a Lego paradigm and play with robotics. There's very little presupposition about what your knowledge is. If you can plug things together, if you can follow pictures, you could build this little robot. But it's not just a toy in that it has sort of this extensibility pattern that beyond the ability to program it or to build it and to program the motors and see things work within the Lego construct, you also have this ability to talk to, if you will, more real-world robotics programming languages like Microsoft Robotics Studio and things. So it's sort of I hate to put it this way, a gateway drug to robotics, right? It's that thing that can get you hooked and pull you into something, but the barrier to entry is really small. The second example is I had the privilege, sort of on a fluke this weekend, of running into my high school science teacher. Happened to be passing through town, and we ran into each other to share a common event. And there's this guy, his name's Randy White. He's a very quiet, unassuming guy, but he's passionate about his technology, and he's very good at transference, right? So he's very good at helping people understand or to develop a desire to learn more. And one of the phrases he used time and time again, it's probably the only thing I remember from his physics class, is start with what you know. He would present this big problem, or at least what seemed to me at the time to be a big problem, or to the class, and he would say, start with what you know. Solve that problem. And the premise being that most of the major problems we need to solve are nothing more than conglomerations of smaller problems and sort of an additive of smaller problems. And if you take incremental steps to solve those problems, you can turn around one day and see that you've solved something pretty significant. So now if you're sitting there wondering, well, what does it have to do with the topic du jour? Well, let's try to tie that together. I view cloud computing as sort of the paradigm and some of the cost models that we mentioned earlier. While you're right, and that would be nice to not have to sort of think about that. And I think eventually we'll get to the spot where it's like buying a cup of coffee. You don't think about the fact that my cup of Starbucks cost me $4. You just buy it, right? It becomes sort of cost of doing business. But I think cloud computing is, in the paradigms as we see with both Amazon and Microsoft right now, that price model opens up opportunities, or accessibility, makes large-scale compute accessible to groups of people that it would never be accessible previously. I think that is amazing, right? Randy White, and I grew up in this. He taught our class, and I grew up in this high school. We had a total of 23 people in our graduating class, so really small high school. There's not a chance in the world that we would ever have a computing lab that we could do work with. We didn't have access to clusters. We didn't know what that was. Yet now with cloud computing, Randy can stand up a lab to actually demonstrate an experiment to do computational physics for pennies or dollars, right? He can do a 20 node cluster for a couple of bucks for a class period. We saw the example during one of the keynotes the other day, where cloud computing enabled them to do this rather significant testing that they would not have been able to do before. And I guess to me the promise is, I work at this massive computing center, and we've had a lot of talks of sort of at the collegiate level and the research center level, but I'd like to challenge us to look sort of beyond that or below that, depending on how you view the world. And let's challenge you to look at ways of how can we expose computational thinking or computational processing from a thought process and massive parallelization, though we certainly wouldn't call it that because they wouldn't get that, but to people to high schoolers, to students at the educational level. How do we provide tools so that teachers such as Randy White, who are simply trying to express physics and computational ideas, can do so with richness, with connectivity to massive data sets. I was talking to a couple of the guys in the back from Microsoft Research earlier. I said, I had the privilege of not growing up in not being trained as a classical scientist and learning that you're not supposed to share data until you've published. And I'd like to challenge the fact. I'd like to see us publish data early and often. Get that data out. Get larger collections of people consuming the data. We saw the talk earlier about Dallas, and one of the key things I think Dallas does, and there's still work that needs to be done there, is to provide a commonality of access to data. So you don't necessarily have to be a domain scientist to access that data. You can be someone who may be a scientist, maybe a science teacher, and have a certain level of intelligence, but you can pull together data from disparate disciplines and do something interesting and use that to sort of open the eyes of that next generation of computational scientists. I think that's where a real challenge lies, and I'd like to see sort of the community step up and address that area.
At this point, I'd like to take questions from the audience, and I'll bring a microphone to those of you. Just raise your hands, and I'll bring it out to you so we can ask our panelists questions.
Thank you. Hi, my name is Rodrigo, and I'd like to propose a theme for the panelists. And the theme is about water and cost. Two of the panelists mentioned that they would like to see a day that the cloud doesn't have any cost. So that would be accessible to all. Or not right there.
Wait. That's what he said. Let me clarify. I don't want it to be free. I don't need it to be free, but I don't want to worry about doing the math to figure out if I should do it locally or somewhere else or whatever. I'm more than willing to pay. He's not.
No.
Okay, just let me just finish the question first. Okay, so the question is the following. We are comfortable with our desktop where we do applications compatible with our CPUs when we are not spending cycles or we are doing things with certain overhead. It doesn't hurt so much. But in the cloud, when we are introducing overhead to cloud applications, the cluster is misused. And my question is, isn't the cloud target environment where we should be especially concerned with performance? Because when you're spending cycles, because we're using overhead in the technology, we're preventing other people from using it. And that maps directly to natural resources.
So first I need to clarify. I'm not suggesting that everything is going to be free. It's just that companies, when it comes to cost, will try to give the infrastructure for free, the platform for free, because they are going to see value from offering additional services. And of course, you will have to pay for those services. I can take, even though Roger asked us not to think about cost and infrastructure and platform, I think when it comes to the environment, the aggregation of resources in data centers that are managed with efficiency and economics in mind is better than having It's better than having thousands and thousands of computers doing processing all around the world when it comes to the environment. When it, you mentioned the performance issue. Again, if the current examples of how cloud computing resources are being used, whether they are internal to an organization or whether they are offered to the public, is that again, from an economics perspective, power consumption perspective, I think sometimes it's better to wait and have scale, and rather than trying to do things fast and get an answer sooner. And again, Google's infrastructure around MapReduce has demonstrated exactly that. People are willing to wait if it is economically better to do so.
Thanks, Abbas.
On the economic side, the cloud has it seems to me, a rather important consequence, which is to go from a purchase model to a rental model. And in the case of software engineering, this could have a major effect on the evolution of the field, because it could get us out of the quandary in which we've been for 30 years. The quandary that I'm referring to is the difficulty, not to say sometimes impossibility, of selling software tools, of selling software development tools. Now I'm exaggerating a little bit because it's not totally impossible, but it is, it is hard. For example, it's difficult to sell reusable components because you get caught in this dilemma of either charging too much upfront or not recouping your investment. And of course, this has been compounded by the whole emergence of free software, and I don't want to go into very politically charged debates here, but the general assumption that software should, in particular software tools, should be free has certainly complicated the picture. And what cloud-based tools, a typical example would be Salesforce, show us is that it seems to be much easier to make customers accept a rental-based model, which, because it's a little money for a very long time as opposed to a lot of money for a small time, and psychologically it's much easier. And this might provide a new impetus for people who want to advance software engineering. It might enable them to find an economic model that supports progress, as opposed to the model that we have had for the past 20 years, which actually has, in my opinion, hindered progress.
Hi there, Kurt van Mechelen from the University of Antwerp. I just want to say that I think you're very right about thinking about cost. This is kind of a problem, I guess, when you look at how these services are right now, let's say, brought into the market. You're not constrained as a user anymore by the infrastructure that's there. You have the choice of different types of architectures, different types of pricing models. So using reserved instances, spot instances, on-demand instances. And this is kind of the complexity, I guess, that a lot of users don't want to think about, and that should be tackled with, let's say, brokering systems that operate on the level of an entire organization, for example, and that kind of optimize this entire portfolio. I think we can learn a lot also from fields of electricity markets, for example, how brokering is done there, to take away this complexity. And this also has a lot to do, I guess, with workload modeling, performance modeling, to kind of automate this allocation process. So I don't know if there's more ideas on the panel in this respect, what could be done there, what are the key questions. But I think it's a very important research topic.
We were discussing about this before we came here, exactly that topic, that there is space for middleware out there that will make it easier for software vendors to build applications that can make those type of decisions based on modeling, based on information that comes dynamically from cloud providers, based on understanding of how the application behaves, the communication, the interaction patterns, the use of storage, and perhaps you can even think of marketplaces where you can have the deal of the day, and you can utilize some computational powers and so on.
Yeah, and I think what's difficult with this problem is that basically you have to solve all these issues that have been along in like distributed computing for tens of years about how you map workloads to infrastructure efficiently. Yeah. And if you really want to minimize for cost, you need to solve all of this stuff alongside with the difficulty of trading efficiently. So I think it's a really complex and difficult problem, certainly to solve close to optimally.
So one thing that I think is important to bear in mind is actually that we cost something for every hour as well. So you may charge 10 cents per CPU hour to use a cloud, but actually most of us in this room are paid, I don't know, 1,000 times that per hour, something like that. Even grad students are paid significantly more than 10 cents an hour. And so unless you are going to produce a code that you're going to run again and again and again, you really do have to make sure that you're not spending too much time optimizing something and wasting your own time doing that, when it actually be, if you took everything into account, cheaper just to run it and then move on to the next thing.
Yeah, I agree completely. So, but this is like thinking about when the cloud infrastructure becomes a real utility, so something that people rely on every day, like they rely on electricity, and so this supports their business. So you can think about workloads that are run often on this infrastructure, and you can learn about how they operate and how you need to map them. And I think it's largely unexplored at the moment.
Just to throw a kink in the argument here, I think the point over here is crucial. That there's when I said I came from industry, I did a lot of software consulting, so it was all about billable hours. You're always thinking about how much am I costing that client, what are my efficiencies and so forth. I think that's very important. I also think that, and this might be slight heresy in this room, but we need to think about how long it's taking us to solve a given problem for a science domain, not how perfect can our computer science be. And because, frankly, at least I view computer scientists as a means to an end, not an end in of itself, right? We're doing what we're doing. We're coming up with algorithms and means of solving problems so we can solve actual problems, right? They're tools. We're building mechanisms to solve that. And this may sound funny coming from a place where people spend years working on squeezing every little last drop of performance out of MPI, but there's a balance, right? You have to. It's reduce. One of the keynoters had a phrase about reducing the time to insight, and that's the key, right? If a scientist poses a question, or a domain scientist, but be it biology or astrophysics or whatever, if they pose a question, we should be looking at how can we help them answer that question in the most fast and accurately possible, not necessarily from a clock time, but from a wall clock time, from the time they pose the question to the time they get their answer. Because I don't frankly care if it takes an order of magnitude longer to run in the cloud, but they don't have to wait in a queue for 6 weeks, then that's a win, right?
Finally, just very quickly, just to add to Paul's point about humans, just resources costing. I think it's great. I think another one to consider is scalability. So it's not the scalability of the infrastructure, but the scalability and complexity of what you're trying to optimize. The questions that you can ask is, would it make sense economically for Facebook's infrastructure, data processing infrastructure, to be outsourced into cloud utility computing effectively? And could you provide the middleware to demonstrate to them that their operational expenses are going to be minimized by using some modeling, some performance modeling related middleware? We are very far away from that happening.
Okay, I had a question about applications, for example, like the smart kitchen and the uploading of data of the vehicle. Like, what will be the security implications of that data, which is I consider to be very sensitive data about every person?
Yeah, so that is an issue. In fact, in the project we have a whole strand of work on trust, and it's interesting how trust differs between older people and younger people. So you'll get younger people who are prepared to put everything on the on Facebook. You know, every picture of them at a party at university. Speaking as a parent who's got 2 children at university, then I find out what they're doing by looking at the photographs on Facebook. And my kids and lots of kids seem very happy to reveal lots about their private life almost in public, whereas older people are much more, in general, much more circumspect about this. So you have to be very careful about what you're doing. For example, on one of the slides I put up, then I deliberately showed medical records being away from the cloud. You know, the idea that you would integrate some information with medical records in order to decide, say, what drug to put a person on given a particular driving behaviour. But you might do that off the cloud in the private IT system of the medics rather than in the cloud if that was an issue, and it often is. I think for some of us who start to look at these things as well in other countries, then the regional aspects of it really vary. So, you know, this idea you upload data into a cloud, then we in a university have particular ethical constraints that we have to meet about what we do with, for example, patient data. Then my country, the UK, has particular constraints as well about where it's allowed to do. And then you've got to look at the small print of the cloud provider for the region in which the data is going into. And so it becomes very, very, very complex. And whether you could, taking the lead from the idea that you could make decisions based on cost automatically, whether you could make decisions based on what data is allowed to go out to a particular cloud and which particular cloud it's allowed to go to based on some automatic matchmaking between the small print of the cloud provider and the particular ethical requirements of the data is something I know some people are looking at, but it's a very difficult problem that you do have to consider.
If I just throw 2 points out there, and this is coming from someone who works at a classified environment with nuclear stuff. This argument comes up all the time. 2 semi-provocative points. There is a certain security through obscurity, which I understand is not, but you have to think through that. If you're blended with billions of other records, finding that data in someone else's cloud is going to be a lot harder than finding it in, say, a hospital's database, right? Secondly, people tend to be, and this is, I don't know your case, but in general, people tend to be arrogant about the way they protect their data with respect to how they think cloud providers protect their data. In general, the cloud providers are going to protect your data much, much better than most data centers that I've ever seen.
Thank you, Rob. All right, so it's now time for us to wrap up the panel. I'd like to thank you, the audience, for your questions and attention. And let's join me in thanking the panelists for their attention. Thank you.